Well, hello everyone, and welcome to Prep 34. So in this prep, we're going to look at two sample tests, both two sample z-tests and two sample t-tests. And the big difference between them is that in a z-test, we are given in the problem description the population standard deviation for each sample. And in a t-test, we are not given the population standard deviation, so we have to estimate it from the sample. So here's our first problem. A corporate manager of a major furniture outlet recently wanted to see if there was a difference in the dollar value of sales between the men and women he employs as sales associates. To research his hypothesis, he selected random samples of sales data. The sales data for men and women at various locations is shown here. Assume the population standard deviation for men is 210. See, that's the given standard deviation that we were just talking about. And for women is 245. At a significance level of 0.05, can the manager conclude that the mean amount sold per day is larger for women? So let's look at the case. Because it's larger means one tail means more, which means one tail right test. So if we want to look at a picture of that, what we're testing to see is if men and the samples for men and women came from the same population, which would be case here where they're both within the blue band, or if the sample for women, which would be the dotted line, actually belongs to a different population. That's what we're testing. So the distribution is Z. The null hypothesis is no significant difference between the mu. And remember, mu means population mean. So the population mean for women and population mean for men. So this is really cool because we're working with samples, but the inference that we're making is all the way back to the population. The alternative hypothesis is that the mean for women is significantly greater than the mean for men. So let's go ahead and get our descriptive statistics for women. So that's going to be the average of this sample. And the standard deviation was given in the problem, which was 245, I think. Yes. And then the count is right here. So 50 records for women. And then for men, the average is here. The standard deviation was given in the problem at 210, and the count is here. All right, so now we have our first graph. And as you can see, the mean for men is 1,603, and for women, 1,751. So it certainly looks like the mean for women is higher. And the big question is this a result of chance, sampling chance, or is this a real difference? And I really want to draw your attention to the little tiny dots, because the big red dot, that's the mean for women. But the little tiny dots here, these are other possible sample means that could have happened for women. So imagine this curve being shifted so that the top of the curve is here, or the top of the curve is here, or shifted this way, top of the curve here, top of the curve here, right? So other possible samples were, and there obviously be lots of little dots in between. I'm just showing some of them. And same thing here with men. This is the sample mean that we found, but sampling error, maybe the sample mean's actually here, maybe it's here, etc. This will become enormously important in the second graph. And the reason it will become enormous, well, I'll explain as soon as we get there. All right, so the sampling distribution of the sample mean, in this case, because it's a two-sample test, the sampling distribution is about the difference between men and women, and the hypothesized difference is, well, they came from the same population, so there should be no difference. So it's 0, and it will always be 0 in these two-sample tests. And then the standard error, it's a slightly more complicated formula than we had before, because it has to take both standard deviations into account, whereas previously we just had to take one, because we just had the true population standard deviation, which was known. In this case, it's not. So it's going to be the square root of what? Okay. Of the sample here for women, standard deviation squared, divided by sample size for women plus, and you really got to get these parentheses right, so please make sure you type it just like this, otherwise you'll spend like 5 minutes here trying to figure it out. Plus the population standard deviation for men squared divided by the sample size for men. Close parentheses, space, and then close the parentheses for the whole square root. And there it is. So basically, this is our expected difference between the two. Our expected difference is, on average. The expected difference between these two, because these are pretty big numbers, is going to be 47, in this case, dollars. But what's actually our observed difference is this minus this. This is 148. So we expected the difference to be around 48, and it's actually 148, so it's almost 3 times the expected. So chances are this is going to be a reject, and you can start to see that over here. All right, now let's talk about these little gray dots in the second graph here. The graph of the sampling distribution of sample mean differences. Notice this word differences, right? Because each of these dots represents a subtraction between a black dot and a red dot. And so if we just had these two, then we'd really only have one column of dots here. But the reason that I threw in these other dots is that you can see where all these other gray dots came from. So basically, in other words, if we subtracted this dot from this dot, right, we'd get one difference. But if we actually picked 2 dots that were almost on top of each other, then we'd get a smaller difference. In other words, closer to 0, because 0 is in the middle. And most of the time, if they really did come from the same population, most of the time, the dots would be kind of one on top of the other. And there would, most of the dots would be here in the middle, which is why the bell curve fills at the middle and then tails off at the end, because the dots over here would be like this dot way out over here minus this dot way out over here. That's a big difference. And so notice the bigger differences come out over here, but they happen less. They should happen less often if they come from the same population. Okay. And in fact, ours actually is way out over there, right? Because from here to here is considered a pretty big difference. You can imagine from here to here would be like even further, way out there. Okay, so then our z-score is always going to be the observed difference divided by what was actually expected in terms of variability, which is 3. So as I said before, we're 3 times what we expected the difference to be. And generally speaking, any number over 2 is normally cause for concern. Or not concern, but cause to perhaps reject on your z-score. So let's go ahead and calculate the probability that we would get that z-score. Z true. And remember, because this is a right tail test, this is going to give me the wrong answer. because I have to, since the answer is a probability, I have to subtract it from 1. So I do 1 minus. And if you're ever wondering, like, where does 1 minus go, that kind of thing, sometimes it's better just to leave it off, get the number, run the function, and then figure out afterwards if it should go inside or outside. But normally speaking, it's always 1 minus a probability. So wherever the probability is, it's 1 minus. All right. So that's a really low probability. So really low probability that these two would be this different if they came from the same population. So this is going to end up being a reject. So my conclusion down here is reject the null, and the p-value is less than alpha, because alpha is 0.05. That was given in the problem. So they come from different. And then the critical value approach, well, actually I can't do that one yet. Kind of got ahead of myself. We got to finish this off. So let's go look at the critical value. So alpha is 5%. There's our rejection region. And here is our critical value over here, which is 1.64. And let's see how we got that. And the way that you do that is norm.s.inverse of the probability gives you the critical values for 2 tail left, 1 tail left. And if we continue this along and then do the 1 minus in here, and so there's our 1.64 because we're 1 tail right. That's the one we're using for this problem. There's the 1.64 calculated there. Okay, and now up here we want to create all the way up here we want to create a confidence interval. Like, well, what really is the true difference between them? Because remember, samples are a little bit inexact. So we start out with the observed difference, and we subtract from that equals that minus the standard error. It's always the biggest number on the page because it's so important, times the critical value for 2 tail. And I picked the 2 tail positive to keep the math straight. And equals that plus the standard error times critical value. All right, so what we would do is go back to our boss and say, look, we think the difference is 148, and it's probably close to 148, but at the minimum, with 95% confidence, at the minimum, the difference is at least 54 and could be as high as 242. And notice the confidence interval does not include the hypothesized mean difference, which was 0, which would have been this line right here in the middle. And when you reject the null, it never will. All right, and so our critical value approach reason, is that 3.10 is more extreme, right? Further away from 0 is what more extreme means. Our z-score is more extreme than the critical value, which was right here. And so our interpretation, finally, is that the mean for women is significantly greater than the mean for men. And since we're rejecting, we are susceptible to a type 1 error, which would be to reject the null hypothesis when it's actually true. Why would that happen? That might happen if we had some really bad sampling error like that the samples for men and women were really off, maybe not true random samples. And then you have some multiple choice questions here, which I will let you tackle on your own, and we'll see you in the next video.